In this lesson, we would understand how to use the algorithm for curve sketching. The learning goal of this lesson is to sketch the curves of a given function using the algorithm that we would be learning in this lesson. And the success criteria for this lesson would be, after going through the lesson, the students will be able to understand the algorithm to follow for curve sketching. The students will be able to apply the algorithm for curve sketching, and students will be able to sketch curves of polynomial and rational functions using the algorithm. Now let's go over the algorithm for curve sketching. The first point is to determine any discontinuities, including vertical and horizontal asymptotes in the domain. We have already learned this in the previous lesson. Second step is to determine any intercepts. This is x or y intercepts that also we went over in the previous lesson. Third is to determine any critical numbers. We know critical numbers are the values of x where the first derivative is 0. So for that we determine the first derivative and put it equal to 0 and solve for x. Then we use the first derivative test. That is basically to use critical numbers and make the table for first derivative test to determine the intervals of increase and decrease, maximum or minimum point, or the point of inflection, whatever is applicable. Fifth step is to determine the end behaviors near the vertical and horizontal asymptote. Sixth step is to conduct concavity and second derivative test. Going back to the fifth step, the end behaviors is something that we discussed in the previous lesson as well. So this was just the table that lets us know how would the graph behave near the end of the vertical and the horizontal asymptote. Seventh step is to complete the sketch using the above information. Now there are points to be noted in this algorithm, and that is, the first point is that not all steps are used in every situation. For example, if we are sketching polynomial functions, then only third step, that is determine any critical numbers. Fourth step, that is use the first derivative test to determine the intervals of increase, decrease, max, min, or point of inflection. Sixth step, to conduct concavity and second derivative test. And to complete the sketch using third, fourth, and sixth point would be the only steps that we have to follow. Let's fix this. So this is third, fourth, sixth, and seventh step is what is supposed to be used for sketching polynomial functions. Whereas for sketching rational functions, we can use all of these steps. When we are answering questions on the test, and if in case we are given a rational function, looking at how many marks the question is worth, the important points. For example, this is an important point towards sketching rational functions. Determining critical numbers and using the first derivative test can tell us whether it is increasing or decreasing. Then finding the end behaviors is important. So we can skip this and we can just move on to seventh step. So which steps to be used are going to be decided on the basis of individual questions. We cannot take up all the different questions. Since we are familiar with the basic shapes of many functions that we have learned in advanced functions, which is the prereq of this course, we can always use that knowledge towards sketching the best possible curve of the given function. In this lesson, we would discuss how we can use the algorithm to make the sketch of a polynomial function. Let's say we're given a function fx is equal to negative 3x cubed minus 2x squared plus 5x, and we're supposed to use the algorithm to sketch this function. Then we would decide which steps to follow. Because it is a polynomial function, we would just follow step 3, step 4, step 6, and we would step 7 to curve sketch it. So let's go over step 3. We was to determine any critical numbers in the given function. For doing so, we would first find the first derivative of this function, and that would be minus 9x squared minus 4x plus 5. We would put the first derivative equal to 0. Since we can factor this because negative 9 times 5 is 45, and we need the sum of negative 4, so we can write it as negative 9 squared minus 9x plus 5x plus 5. And we would group it and we would find out the common factors such that we are left with x plus 1 in the bracket. Then we can factor 5 out and we are left with x plus 1 in the bracket again. The common factor of these two terms is x plus 1, and we are left with minus 9x plus 5. And finally, we will be left with these two factors that we will be solving for x from. When we put x plus 1 equal to 0, we will have x equal to negative 1. And when we solve negative 9x plus 5 is equal to 0, it would give us x equal to 5 by 9. So these are our two critical numbers. And we've done the third step. Step number 4 is to conduct the first derivative test. And for that, we will create the table. We know the critical numbers are negative 1 and 5 by 9. So we would use this to write on our intervals. It's negative infinity to negative 1, then negative 1 to 5 by 9. Then we have 5 by 9 to positive infinity. And we would write down how the derivative would be to conclude our increasing and decreasing intervals for the original function. Because the derivative function was minus 9x plus 5, x plus 1. Now to determine the sign of the first derivative, we would pick any number value that lies in the interval and sub it in the derivative function to get the sign of the derivative. Let's say we pick a negative 10 here and we sub it in the first bracket. Negative 10 times negative 9 will give us a positive 90. Plus 5 gives us a positive value here. When we sub in negative 10 here, we get a negative answer. So positive times negative will give us a negative product. When we pick any value from negative 1 to 5 by 9, as 0 lies in between this interval, so we would use 0 here. Negative 9 times 0 is 0, plus 5 is a positive answer. Here 0 plus 1 is a plus 1, which is also a positive answer. So the derivative function is positive. If we go from anywhere in this interval, let's say we select 10, we sub that in here. So we get a negative 90 plus 5, which is a negative answer, and negative and 10 plus 1 is a positive answer. So negative times positive is again a negative. This means the original function is going to be decreasing in the first interval, increasing in the second interval, and decreasing later on. Exactly at negative 1, we would notice, because it's decreasing, proceeding, and following increasing, so we would notice a min point. Exactly at 5 by 9, we would notice a max point. We can also use just this much information to make the sketch. However, we have to use all the steps that apply in this case in order to get full marks towards this question. So next we use step number 6, where we have to conduct concavity test and the second derivative test. We'll proceed forward from the first derivative equation that we got as negative 9x squared minus 4x plus 5. So the second derivative in this case would be minus 18x minus 4. Doing the second derivative test, all we have to do is just use the critical numbers in the second derivative equation. Here we have the first critical number as negative 1. Sub it in the second derivative equation. This would give us an 18 minus 4. That would be a 14. Since it's a positive, second derivative test says that at negative 1, we would see is called a minimum. Then we solve for the second derivative at x equal to 5 by 9 and sub it in the equation. So when we simplify it, we get a negative 10 minus 4, which is a negative 14. Since at 5 by 9 we see a negative answer, so at 5 by 9 we would see a maxima. So this and this are aligned. That means both of these tests are in alignment to each other. So this is a confirmation that we have a minimum at negative 1 and maximum at 5 by 9. To determine what is the exact minimum and maximum point, we can always sub in negative 1 in the original function, that was negative 3x cubed minus 2x squared plus 5x. So we would just replace this in place of x, and when we simplify, it will be negative 4. So we can say the minima point is negative 1, negative 4. Similarly, when we solve for f of 5 by 9, we would get the value of 1.6. So that means the maxima point would be 5 by 9, 1.6. Now the last thing we have to use is the concavity test, and then we'll put everything together to make the sketch. For concavity test, we have to solve for the second derivative function that we got as negative 18x minus 4, and we put it equal to 0. So we get negative 18x is equal to 4, x is equal to 4 by negative 18, which is negative 2 by 9. We use this negative 2 by 9 to make the interval table, and the intervals we have is negative infinity to negative 2 by 9, exactly negative 2 by 9, negative 2 by 9. We're going to use this to find the sign of our second derivative and make a conclusion about the original function. When we sub in any value that lies in this interval in the second derivative equation, let's say we put in a negative 10, so it will give us a negative 18 times, which is a positive 180 minus 4, so this gives us a positive answer. Exactly at negative 2 by 9 we see a 0, and anything from this interval we would see a negative sign, negative value of the second derivative. So we would make a conclusion for the original function. That is, when we have a positive second derivative, the original function is concave up. Here it's concave down. And here we would see the point of inflection. That is the change point between concave up and concave down function. Putting all these things together, we will just summarize what we have drawn out. First step, we got the critical numbers, and that was x equal to negative 1 and x equal to 5 by 9. Then we found out that from negative infinity to negative 1, the function is decreasing. From negative 1 to 5 by 9, the function is increasing. And then 5 by 9 to positive infinity, the function will be decreasing again. We also found out that the minima is going to be seen at negative 1, negative 4. And maxima is going to be seen at 5 by 9, 1.6. From step number 6, we got to know that point of inflection will be seen at negative 2 by 9. To determine its y value, we will just solve for f of negative 2 by 9 by subbing in negative 2 by 9 in the original function, and that would give us a value of negative 1.2. So point of inflection will be negative 2 by 9, negative 1.2. Also, we have found out that from negative infinity to negative 2 by 9, we would see the graph to be concave up, and from negative 2 by 9 to positive infinity, it would be concave down. So we would use all of this information to make the sketch of the given function. We always start by first plotting the max, min, and point of inflection points. So this is negative 1, and this is, let's say, negative 4. This is our min. Max is 5 by 9. When we change it to decimals, it should be 0.6. If, let's say, 0.6 is here and 1.6 is here, then this will be the max point. Point of inflection would be at negative 2 by 9 minus 1.2. Negative 2 by 9 is approximately negative 0.2. That would lie somewhere here. And if, let's say, negative 1.2 lies here, so this will be the point of inflection. Because the graph from negative infinity to negative 0.2, that is this point, would be concave up. So this is how the graph is going to look like. It's concave up. Reach the minima at negative 1, negative 4. Hit the point of inflection. Reach the maxima. So this is all the way concave up. Then becomes concave down from negative 0.2 to positive infinity. And this is how the graph is going to look like. We can also say that the point of inflection is nothing but where the concavity of a graph changes. So this section of the graph looks concave up, and this section of the graph is concave down. And if we notice that from the first derivative test, from negative infinity to negative 1, the function is decreasing. That's what is happening. From negative 1 to 5 by 9, the function is increasing. And then from 5 by 9 to positive infinity, it is decreasing. So this graph obeys all of these rules. So this is the most appropriate sketch for the given function.